بسم الله الرحمن الرحيم. اليوم راح ناخد محاضرة في الاوبتمايزيشن عن موضوع في الكلاسيكال اوبتمايزيشن اللي هو Lagrange Multipliers. وفي هذه الحالة عادة بيكون في عندنا function f of x and y equals z، وفي عندنا constraint g of x and y equals c, constant. So the function here is a surface and the function here is a curve. And notice that the constraint here is equality. It's not inequality, it's an equality constraint. Okay, let's visualize what's happening here. If we assume that we have this function to be optimized that has those level curves, so those are level curves of f of x and y equals c1, c2, c3, etc. So to find the level curves of a function, we fix z to a certain value, draw all the values that have the constant c to be, the value of c to be constant at this value. We have all those with a certain value of c. The second one is second c, third c, and so on. So those are called level curves, or sometimes we call them contour values, contour shape or contour plot of the fx of x. So it's either level curves or contour plot of f of x and y equals z. So those are contour plot or level curves. And g of x and y is another curve that has some other shape. And let's do it with the red line. And we will assume that it will touch this level curve like this. So if we assume this is to be our g of x and y to be equal c. Notice that the level curve here, or the curve of the constraint, touches the level curve of f of x at a certain c. Now those two curves here, they exactly have the same slope. So their slope is equal. And once their slope is equal, so their normal to the slope is also proportional to each other. So they have exactly the same dimension. So once this curve and this function, they have exactly the same slope at this level curve here, then both of them have the same or proportional normal to each other. So let me just write this down. So the slope of f of x, y equals z is equal to the slope of g of x and y equals c at this point here. So the slope at the point where the g of x and y equals c touches the level curve here, they make exactly the same slope, or the normal to the level curve of f of x and y equals z is equal to some constant times the normal of the normal of to the level curve of g of x and y equals c. Okay, so let's take this lambda outside, put it in a nice form like this. Okay, so the normal to the level curve is proportional to the normal of the level curve of g of x, and this lambda is called the Lagrange multiplier. The Lagrange multiplier. Okay, what is the normal to the level curve in mathematics? It's the gradient. So in other words, we can say that the gradient of f of x and y is equal to lambda times the gradient of g, the gradient of g of x and y. Okay, so this is the end result, and here we have this lambda. If we have more than one constraint, then we will have more than one lambda. So we'll take two lambdas, and you'll see this in the next example. Let me just first take an example to demonstrate this idea of Lagrange multiplier. So let's take an example and try to find the minimum or the maximum. Let's find the optimum point, f of x and y equals xy, with the constraint z, 2x plus 3y equals 6. So we need to optimize this with this constraint. Okay. To do this, I'm gonna find the gradient of f equals the first derivative with respect to x is y, the first derivative with respect to y is x. So this is our gradient here. What is the gradient of g of x and y? Is equal to 2 and 3. So to apply this equation, so we have x equals to lambda times 2 and 3. From this, we can say that we have y equals to 2 lambda and x equals to 3 lambda. To solve for this one, we have to go back to the constraint and make the constraint to be equal to 6. So using this equation here, which is 2x, and x is 3, 2 times 3 lambda plus 3 times y, which is equal to 2 lambda equals 6. So you have 12 lambda equals 6. Lambda equals 1/2. So for lambda equals 1/2. So we have one single lambda here. Going back to the equation, solving for y and x. So x equals to 3 lambda, which is equal to 3/2, and y equals 2 lambdas, and this is equals 1. Okay. And you will have f of x and y equals to x times y, and this is equals to 3/2 times 1, and this is equal to 3/2. So this is one-to-one example. And you can see that this one is minimum or maximum. You can check that out. X is with this value at 6. X times y, you can see that if you take x to be 0, y to be 0, then this one is not. Let me see. How can we prove this and see if this is a minimum or a maximum? 2x plus 3y equals 6. This is a line. If x equals 0, so if x equals 0, you have 3y, then y equals 2. So if x equals 0, y equals 2. And if y equals 0, then x equals 3. So you have this line here. And our point is 1 for x equals 3/2, 1.5, which is halfway here. So any point on the line with x, if we assume x equals 2, then y equals 0, then y is equal to 0. So I would assume that this one will be something like this. So the function for y equals 2 and x equals 0, it satisfies this constraint, and the fxy here, let me just put it in this way. f of 0 and 2 is equal 0. F of 3 and 0 is also equal 0. But f of 1.5 and 1 equals 3/2. So I would assume that this one is a maximum. You have zeros here, you have this value here. Okay? So probably you'll have negative values in this here and this here. Okay, so this is a solution for an optimum point with Lagrange multiplier. Let's take another example and see how we deal with things. One more example. Example 2. F, x, y, and z equals to x plus 2y minus 2z, 2z with x squared plus 2y squared plus 4z squared equals 1. So we have only one constraint, equality, so we can apply the Lagrange multiplier. We need the gradient of f of x and y and z, which is equal to the derivative of x, 1, 2, and minus 2 with respect to z, and the gradient of g of x and y and z equals to 2x, 4y, and 8z. So this is the gradient. Now we have to apply the equation of the gradient of fx, y, and z equals to or proportional to the gradient of g at the point of optimum, minimum or maximum. So those two gradients, which are the normal of the level curves of f and g at the same time, should equal to 1, 2, and minus 2 equals to lambda times 2x, 4y, and 8z. From those two equations, actually, you can notice that you have three equations and three unknowns, but lambda is also unknown, so you have to go to the constraint for the fourth equation to be satisfied. So you have four equations. The first equation says that 2 lambda x is equal to 1. This is from the first equation, so you have equation number 1. The second equation says that 4 lambda y equals 2, second equation. Third equation says 8 lambda z is equal to minus 2. So this is the third equation. And the fourth equation is x squared plus y squared, 2y squared plus 4z squared equals to 1. This is your fourth equation, which is the constraint itself. Constraint itself. Okay? Now, from the first equation, we can say that x is equal to 1 over 2 lambda. From the second equation, y equals also 1 over 2 lambda. And from the third equation, we can say that z equals minus 1 over 4 lambda. Okay? Minus 1 over 4 lambda. If we apply this in the constraint itself, then you have 1 over 2 lambda squared plus 2 times 1 over 2 lambda squared plus 4 times minus 1 over 4 lambda squared equals 1. So you have 1 over 4 lambda squared plus 2 over 4 lambda squared plus 4 over 16 lambda squared equals 1. So we take this, so with 4, so you have 4. So we end up with 4 lambda squared as a common denominator. So you have 1 plus 3 plus 1 equals 1. So you have lambda squared equals 1 or lambda equals 2 plus or minus 1. So you have two solutions actually. We have to look for those two solutions and see what will happen. Okay. So for lambda equals 1, if lambda equals 1, then x equals 1/2 y equals 1/2 and z equals minus 1/4. Okay, if you apply this to the function, which is equal to f of 1/2 minus 1/4, this will equal to 1/2 plus 1 minus 1/2 plus, or minus, sorry, minus, so this is plus 2 times 1/4, it's 1/2, so this is equals to 2. So if for f of 1/2 minus 1/4, it's equal to 2. For lambda equals minus 1, then x equals minus 1/2, y equals minus 1/2, and z equals 1/4. So f of minus 1/2, and 1/4 equals to minus 1/2 minus 2 times 1/2, or plus 2 times minus 1/2, and at the end is minus 2 times 1/4, and we end up with minus 2. So for this point, f is maximum, and for this point, f is minimum. Okay, f is minimum. Okay, let's try to see the problem with another prospect. So we will define for this problem the Lagrange multiplier with two constraints. We'll have as an example f of x, y, and z equals to x squared plus 2y minus z squared, with the constraints g1 of x, y, and z equals to 2x minus y equals 0, and g2 of x, y, and z equals to y plus z equals 0. So in this problem here, we have two constraints. We have the function that we need to optimize, this constraint with equality equal to 0, this constraint with equal to 0. What we will tackle this problem in a different way. We will define here a function. We will define the Lagrangian function. What is the Lagrangian function? The Lagrangian function L is equal to f, the function itself, minus, if you have one constraint, then it's minus lambda times g. This is for one constraint. Okay, if you have one constraint, then f lambda, and you find the derivatives with respect to each parameter inside and with respect to lambda, and you equate it and you find the critical points. If in our case here, for two constraints, then the Lagrangian L is equal to f minus lambda 1 g1 plus lambda 2 g2. If we do this for our problem here, then we have x squared minus, plus 2y minus z squared minus lambda 1 times the first constraint, which is 2x minus y minus lambda 2, which is the multiplied by y plus z, and this is our Lagrangian function. So the Lagrangian function is the making a big objective function or performance index. It contains the function that you need to minimize minus lambda 1 with the first constraint to be equal to 0 and minus the second constraint multiplied by the Lagrangian multiplier, and the equation itself should equal to 0. So by the end, the constraint should be satisfied. So this one will be 0 and this one also will be 0. And you need to minimize the function or maximize the function itself. Okay, now the next step is to take the derivatives of the Lagrangian function with respect to every parameter inside. Notice that you have 1, 2, 3, 4, and 5 parameters. So to solve this question, this problem, we need to find 5 equations so that you have a unique solution. So the first one will be Lx, which is the derivative with respect to x. So this one, Lx, so this is 2x and minus 2 lambda 1. This equals to 0. And from this equation, we can find that x equals to lambda 1. The second equation is Ly, which is equal to 2 plus lambda 1 y minus 1 times minus lambda 1, so this lambda 1, and you have here minus lambda 2 equals to 0. And I will keep this one until the end. I'm going to use this one to solve the problem. Just keep it. Yeah? Let's just keep this one. Lz is equal to minus 2z minus lambda 2 equals 0. And here we have z equals to minus 1/2 lambda 2. L with respect to lambda 1, so the derivative with respect to lambda 1 is equal to the same constraint, 2x minus y equals 0. So we can figure out that y is equal to 2x, and if x equals lambda, then y equals to 2 lambda 1. And L lambda 2, it's y plus z equals 0. And this means that you have z equals minus y. And this z equals minus 2 lambda 1. Okay, so you have lambda z here and z here. We can say that minus 2 equating z from both sides, so z equals minus 1/2 lambda 2 equals minus 2 lambda 1. It means that lambda 2 equals 4 lambda 1. Okay. Going to equation for Ly, this equation here, then 2 plus lambda 1 minus lambda 2 is 4 lambda 1, so minus 4 lambda 1 equals 0. أهلا. شكرا. So we'll continue. So from this we can, to find lambda 1, so lambda 1 can be equated to be 2/3. Lambda 2 is equal to 4 lambda 1, so it's 8/3. And from those values we can find x equals 2/3, y equals 4/3, and z equals -4/3. And f of 2/3, 4/3 minus 4/3 equals to 2/3 squared plus 2 times 4/3 minus -4/3 squared, and this is equals to 4/3. Okay, this is how we solve a problem with two constraints. I'm gonna leave you with a practice that is a homework that you have to do it by next Thursday, not tomorrow. So this, let me just put it as homework. F of x, y, and z equals to x squared plus y squared plus z squared, with the constraints g1 of x, y, and z equals to x plus 2y plus 3z minus 6 equals 0, and g2 of x, y, and z equals to x plus 3y plus 9z minus 9 equals 0. Use Lagrange multiplier to find the critical points and points, and find the minimum or both. Okay, with this homework, so this is due Thursday. Solve it and examine yourself if you got the topic for Lagrange multiplier, and I hope you did. Thank you very much, and we'll see you in next lecture.